Hello everybody, welcome to my class. Today I'm going to explain about what is uh, product rule and quotient rule in derivative. All right, and definitely I will produce some examples also where those rules are applicable. So let's share the screen. Okay, so here you can see the topic derivatives, where I'm going to explain mainly about what is product rule and what is the quotient rule, and how those sorts of rule are applicable to the problem area. All right, so I will also discuss about the necessity of these two rules. So here, in order to prove these two rules, so first of all, let's suppose that u and b both are the functions of x. You can write u equal to fx and b equal to gx. And if you encounter any sort of function like y in terms of the product of two functions of x, in that case, it is found that the product rule is given by this way. All right, so this is the product rule. And if your function is in x are represented in this way, then you have another rule that is called the quotient rule. All right, and you can also see that here in this case, for example, if y equal to uv given, for example, if y equals to given uv, and you know that both are the function of x, that means you will have this sort of thing like this: x squared plus 2 maybe, and then times another function of x. You can say this is root x plus 5, for example. All right, and for example, even if you have put the root of all this sort of thing, so this way you can although multiply these two and find the derivative of the function y equal to fx in this case. But the difficulty arises when you see something power like this, for example, root 2. It can also be expanded, but it takes a lot of time. All right, so therefore, instead of wasting the time, we can find the derivative easily by using this sort of rule. So here you can see this is the product of x under root of x squared plus 2 times root x plus 5. Okay, so this is called the product of the functions of x. And here, for example, at this time, your function would be like this. So y equals to u by v. That means it is in the division form. Therefore, this is called the quotient. And your function will be something like that. So same thing I'm taking this way: x squared plus 2, and these are under root. So you can write power half, or you can write under root. All right, and instead of multiplying, now you divide by the another function of x, that is root x plus 5. Okay, so these sort of things are the quotients. So in order to find the derivative, that means the dy by dx for the function like this, we have to use the quotient rule. And if you are going to find derivative of function like this product, you have to use the product rule. So also, before going to explain further about these rules, for example, here you can see it is given that u equals to fx. So if you find the derivative of u, you can say this as du by dx equals to dfx by dx, means you can write here f dash x, and it can also be written like this. U means you can say it is u dash equals to f dash x. Okay, and similarly, for example, your v is given as in term of again another function of x. All right, so therefore you have dv by dx equals to, we have derivative of v, that means d is the function of g is the function of x, that is equal to gx equal to v. So that means you can see that g dash x, that means you have taken the derivative of this function g. Okay, and this can also be written like this: v dash equals to g dash x. Okay, so all those sorts of are the thing that we can use as the symbol. And now let's go to the main part of the proof of these rules, is that Okay, so first I'm going to do the product rule, right? So the product rule in derivative. Okay, so you can see that product rule looks something like this. So we have to prove this sort of formula. So we have y equals to u times b, and you have we have just seen that u and b both are the functions of x, and if you like you can also write y equals to fx and b equals to gx. And now you know by first principle or by definition in the derivative, you should have knowledge of this sort of thing first of all. So video for the first principle or by a derivative by definition is also here in this RBS channel. So you can check through the playlist. You'll be able to find this sort of rule, this sort of principle. So by definition, okay, we have, for example, dy by dx. If you are going to write dy by dx equals to, it's going to be limit delta x tends to 0, and then it is f x plus delta x. You can find this in different form. Sometimes it is mentioned that instead of s tends to 0, delta x tends to 0, there will be s tends to 0 also. So this is one of the way that we do here, and divided by delta x. It's okay, but actually we are going to find d by dx. That is dy dx means dy dx of the function u times v, right? That means u times v means you can say that gx times or fx times gx. So if you proceed further from here, and this is delta x, so you can write here limit delta x tends to 0, and upside you can see that there is increment in x, so we write increment in x only and fx only. So you can see that here it is in fact, in general, it is in fact like fx, isn't it? So there is x plus delta x means we are talking fx, we are talking is y. So at this time, fx means we have fx gx, so we have to use both this fx as well as gx. So in that case, what you can write here, f x plus delta x, and then another function g x plus delta x. In place of fx only, we have both the things, fx and gx in place of y. So in fact, it is y plus delta y, and this is y. Okay, so that what we have write, instead of writing only fx, you have to write here both fx and gx, because y itself is in terms of fx times gx. And then whole thing is going to be divided by delta x. And then after that step, you have here, you have to adjust a bit there in terms of fx only and in terms of gx only. So let me check out this. So upside, what I'm going to do is that fx plus delta x, and this is g x plus delta x is already there. So one new term I'm going to introduce over here is that minus fx times g x plus delta x, and then same thing as I have put this extra, so I have to balance this term by the same thing. So plus fx times g x plus delta x. Okay, so we have to balance by the same term, and you can see here we have already minus fx times gx. And even though I have introduced that sort of term, you should be able to understand that why I introduced this sort of term like fx times g x plus delta x. Okay, so it will be clear once you pay attention here, and whole thing is divided by delta x. And after that, if you move further, then you'll have, yes, limit delta x tends to 0. So what can you do in this case is that, look at here, from this term to this, if you compare from here to here now, what are you going to take out common is that gx plus delta x, and here also gx plus delta x. So if you take out that sort of thing common, that means you are going to take gx plus delta x as common. Then inside the bracket, you are left with here f x plus delta x, and here minus fx. Okay, and then this is delta x term, so we'll divide them by later. And then we have another term also common somewhere, so say this is plus. So between this and this, what can we get common? You can see that fx fx are common, so it is here plus sign, so take care of the algebraic sign also. So we are starting from here, so it is plus fx. If you take out common at this time, then this is going to be inside the bracket. Here fx is taken common out, so it is g x plus delta x. Then there is minus sign, you can see here. See minus sign, as fx is out, so it is remained with gx inside, and whole thing is divided by delta x. Okay, and from this term you can see, if I go further, so limit delta x tends to 0 in this case, so gx is here, so gx plus delta x, and then inside the bracket what you can write is that here in this case f x plus delta x, and then this is minus fx. Okay, and this sort of thing is going to be divided by delta x over here, and then the limit is applicable to another term also. Just so I'm just doing the fraction separation algebraically here, so that it will be the whole thing from here to here, you can say. Okay, so you can say that from here up till here there is one term, so we divide by delta x. Now we separate another term, and we can also divide them by the term delta x after that. So after this step, you can see that this is limit is again applicable here. So either you write one time limit or many time limit, it doesn't matter. So wherever you find delta x, then you have to remember that, or you have to know that the limit is applicable. So in that case, it's going to be fx. Then inside the bracket, you have g x plus delta x, and then it is minus gx, and then the whole thing is here going to be divided by delta x. All right, so let me have this space clear. Okay, now, so what you could see in this case is that, so after this, if I am proceeding the step after this over here, then what you can get from here is that equals to, yes, you can see there is, now let's put the limit back over here. So what you can write here in this case, that limit, we are taking it back, so gx plus delta x, and then times it is limit to the function, this function f x plus delta x minus fx divided by delta x. All right, so we have one term like this, and we'll have another term like this again. So here you can see there is plus, so we can write here plus, and you can apply the limit where it is applicable. So you can write the limit again, the limit delta x tends to 0, there should be tends to 0, and another term you can see that fx doesn't contain here delta x, so we don't need to put anything for fx. So just we keep fx over here outside. This is fx, okay, because it doesn't require the limit, so limit goes to here, like g x plus delta x minus gx over, this is delta x. And after this step, you can see that. So as you have here gx plus delta x, so delta x is there, so you can put the limit over here. So here you are remained with here gx and times, and you know that by the definition of derivatives, this sort of term when limit delta x tends to 0 is now called, it is like here f dash x. Okay, that sort of thing is called f dash x if you are talking of y equal to only fx. All right, and here I have used the pattern for the same. So in fact, this is the derivative of y. So here, this is the derivative of the function gx. So what it is, fx. So what is it? This is f dash x. Okay, and after that you have plus. You can see there is fx. Okay, and in the similar way, you can see that this is the derivative of the function gx by definition of the first principle. So you can write instead of gx, it is g dash x. And after that, you can reshape the things like this. Let me write fx first of all. It is fx, and then you can write here g dash x, because this is plus, so you can write in either way. So that this is fx, and then this is here, no, here fx g dash x. So this should be gx. I've used just a plus b equal to b plus a like that. So it is this is gx times f dash x. So what did you see here is that as you are going to find the derivative of gx times fx times gx, that is u and v in product form, in that case what you have got is there is no derivative for first function. For example, this is u, and there is derivative for the second function of x like this. And here also gx is the, and then another time plus no derivative for the second function, but the derivative for the first function. And this sort of thing you can also write like this. Here, this is u. All right, so fx equals to, we have supposed u, so here you can, it is u, and then for g dash x you can find, because gx itself is v, and this is u, so this is no derivative for u, so we just write u, and g dash x is the derivative of v, so you can write dv by dx, and plus after that this is v, and similarly it is du by dx. Okay, so this is du by dx, and hence let's check whether or not we have arrived to this step. Yes, we have got the same step like this, and this is called the definition of, this is called the derivative of the given function by product rule, and hence this is proved. So in order to explain the application of this product rule, let's find dy dx for this function. You can see this is first is the function of x, that is in form of u, and this is again the function of x, that is v, and you know that dy by dx formula in this case that we have just seen here is that this is u dv by dx plus v du by dx. All right, it means that no derivative or nothing for u but derivative for v, plus nothing for v but derivative for u. And you have here in place of u, you can say that it is under root of x squared plus 2, and then in place of v, so this is the place of dv by dx, so dy dx of v, so it is root x plus 5, and in between there is minus, you can see in the formula, and v value is root x plus 5, and then dy dx, this is the place where we differentiate the function u, and which is, it is x squared plus 2. Now use the usual way of finding the derivative here, so we just keep like this, so it is under root x squared plus 2, but in the bracket you can see that this is the root, and if you are efficient in calculating the value of derivative of this root x, so it's going to be 1 by 2 root x and the derivative of 5 is going to be 0. And then plus it is root x minus plus 5. So we do nothing for this because according to the formula, we should keep as it is. And now after that, you can see there is a power. So you cannot take this sort of thing directly, derivative. So what you can do here in this case is that you have to apply the power rule that you might have learned before. So here in this case, if I'm applying the power rule, and the difficulty was caused because of the whole thing power is 1 by 2. All right. Therefore, we needed to go through the product rule. Otherwise, we could expand the term if that there will be a square or cube. But if there is higher power or difficult power like 1 by 2, 1 by 5, it will be difficult, and it will be very much time taking. So in order to save the time also, and also in order to make our work easy, we have developed this sort of formula that is called the product rule. We have means the mathematicians have developed this sort of formula. So it is, take the this is x square minus 2. So this time I am taking the power rule now. So you should have knowledge of this sort of power rule, and then times this is d x squared plus 2 over dx, all inside the bracket. Okay, and then proceed further. Just keep writing this sort of thing, or otherwise if you multiply these two, then it is under root of x squared plus 2 and divided by 2 root x, and then it is plus, you have here it is under root x, and then plus 5 is outside of this root, and then we have inside this bracket, look at here, this is like root x, so it is going to be derivative for this function. You should have knowledge of finding the derivative in general. So it's going to be 2 root x squared plus 2, and then times, we are here now, so it is derivative at this point is, it is 2x, and there is a constant term, so constant has derivative 0. And after that, you have under root x squared plus 2 by 2 root x. This is 2 root x, and then plus, again you solve it, so it's going to be 2x times, upside it is root x plus 5, and I think you could cancel this 2 and 2 also, so we have only x here, and then divided by under root of x squared plus 2, and this is the answer. If you like, you can solve it further algebraically in order to check how the answers are expressed in your book. Otherwise, you can just leave your answer as it is. Okay, guys, let's now prove how the quotient rule formula can be obtained. So quotient means, just earlier we have seen when a function is expressed like this, u by v, or also you can see say that is equal to fx by gx, for example. In that case, dy by dx of this sort of quotient is what? All right. So we have, again by definition, we can say that by definition means by first principle, okay, of derivative. By definition, we have in general dy by dx, that is also called sometimes f dash x if the function is represented in term of fx. Otherwise, if the function is represented in term of tx, you can say that t dash x. Okay, no problem for this. So in general, what is our formula by definition is that limit delta x tends to 0, f x plus delta x, that is increment in x and y respectively, we can say. So this is by fx by delta x. Is that okay? So here in this case, we can see that okay. So here how we keep them is that here we have dy by dx equals to dy dx of, we are going to find the derivative of fx by gx in fact. Okay, so if you use this definition, then you can have like this. You can say it is limit delta x tends to 0, increment in x means what you can write here, fx plus delta x means fx plus delta x, but we are also dividing by gx, so we write here gx plus delta x, and this is the place of fx only, but here in place of fx we have to write fx by gx, so we write here fx by gx, and the whole thing is going to be divided by delta x, you can see in this formula. So good idea is to write delta x this way. So if you write times 1 by delta x, it also works algebraically. And then let's go further than that. So this is limit delta x tends to 0. You have to keep on writing the limit until you until the limit has been used up. So it is 1 by delta x, and then we do the general algebra here. So in that case, our derivative is g x plus delta x, and then its LCM is, and then this is gx. And now by using this simple algebra, so what we can write here, this is gx times f x plus delta x, right? And then plus it is fx times, you can write g x plus delta x algebraically, right? And then it is limit delta x tends to 0, see 1 by delta x, and then inside the bracket, let's see here, we'll do the same sort of strategy that we did while proving the product rule. So here you have to check that what is the way where we can get the term like fx plus delta x minus fx by dx, maybe gx plus delta x minus gx by dx. Okay, so this is delta x. Okay, so what I'm doing here is that it is gx f x plus delta x, and if I require fx by taking gx common out in order to make the term like this, what I will do here is that I will write minus gx times fx, because from this term if I take out gx common, then I will have the term like this, fx plus delta x minus fx, and hence this is divided by delta x would be f dash x. Okay, and as we have taken this term extra, so we have to balance by its opposite sign, so it is gx and fx. All right, and then remaining terms are, you can see here is that, yes, remaining term is here fx, so it is plus fx and then g x plus delta x. All right, and then proceed further. This is limit delta x tends to 0, this is 1 by delta x. So from here till here you can take gx common out, so this is gx, and inside the bracket you'll have it is f x plus delta x term, and then minus fx. Okay, as gx has been taken common out, so it is fx. Okay, and then it is plus, but when you take gx common, fx common, it's going to be fx. Yeah, at last it should be not plus, it is minus. Okay, so this is minus sign. All right, so let's take this minus sign in front. So if you take the minus fx common from these two terms, yes, and then inside the bracket you'll have first minus is plus, so it is g x plus delta x, and then this plus will become minus, negative sign, so this is minus, fx is taken common out, so this is gx. Okay, now algebraically you can divide by delta x to both of these terms in between this minus. So do the same thing over here, and limit goes to the both terms because it applies to, we have to use the limit where it is applicable. So that what you can write in this case is that gx, because there is no delta x in gx, so we can take it outside of limit, and then limit delta x tends to 0, and we have this term. So it is f x plus delta x minus fx, and this delta x we divide over here, and then plus limit goes till over here, and here also you can see that there is no delta x in fx. So what you can write in this case is that you can just put it outside the limit. So this sort of limit you can see, not like algebraic multiplication, okay, note that. So whatever it is applicable, you can write this limit. So it is not necessary that you write it only one time or two times. You can write as many times you need, but make sure that we are not multiplying or dividing by this limit algebraically. So it is fx, and the limit is applicable to now another term. This is delta x, and then it is g x plus delta x and minus gx. You know, we have been missing out one term from these steps. You can see in the denominator there is, every time there is here g x plus delta x, yes, and then this is gx. So here also there is g plus delta x. So what you can do here is that you can write them aside, and here you can write here gx as limit we have inserted in. So in place of delta x limit, you can take it here as 0, then another gx is here, okay. Similarly, we have here at this point whole thing divided by g x plus delta x, and then this is gx, all right. And now proceed further. What happens? Let's see. Equals to, now we already have here, it is, yes. So upside, first of all, let's see. If you consider this sort of term, what are you going to have here is that it is in fact f dash x, all right. And this term is in fact by definition of derivative divided by delta x, okay, because delta x gets algebraically divided. This is delta x, yes, this is delta x, and delta x is divisible over here also, okay. So that is going to be f dash x, and that is going to be g dash x. And finally you can see that what we have got like this, gx, there is nothing to gx, but for this sort of term you can write f dash x, that means derivative of the function fx, and there is the term minus, so it is minus, and we have fx here, we have fx here, and then it is this sort of term is in fact g dash x, that is the derivative of function gx. So what you can write here, it is g dash x, and then whole thing is divided by, you can see here that this is gx plus 0 is 0, so it is in fact gx, and gx times gx is gx squared, gx whole squared, yes, gx whole squared. All right, so in this way we could prove the quotient rule formula also. But if you would like to express that term of u and v, you can do so also. Is that, yes, after that what you can write here, you can see that we have u equals to fx and v equals to gx, so that we have g dash x equals to du by dx, and also here f dash x equals to du by dx. So if you express like in term of u and v, so what you can do, that gx means you can write here v, and then it is f dash x means derivative of u, and then in between there is minus fx is just as it is fx, so that in place of fx you could write it is u only, okay. So that is u, and then g dash x means derivative of v, you can see here, this is v, sorry, derivative of v, so it is dv by dx, and the whole thing is going to be divided by gx square, and g itself is v, so you can write here v square, and hence the quotient rule is also proved. Now let's do an example where this quotient rule is applicable. So let's now apply the quotient rule in the problem area. So for example, here in this case, if you are given as y equal to, in the form of quotient, in the form of fraction, in fact, in that case, the quotient rule is applicable, and especially when you can see that upside is okay, power 1, even 2, 3 is fine, but when the power becomes 1 by 2, 1 by 3, or even more than 4, 5, 6, yes, then in that case, the algebraic difficulty will be high, and also it consumes a lot of time in order to go to solve it further through algebra. So good idea is that to apply some sort of rule that makes our work easy. So at this time, as we have now knowledge of the quotient rule, means then we apply that formula. So you can say that the numerator as u and numerator as v, and you know that you can write, we know when y equals to, given in terms of u by v, both u and v are the functions of x, then dy by dx is going to be v, then du by dx, minus u, then dv by dx. After that, whole thing is going to be divided by v square, and then we place u and v in their respective places in the formula. So in place of v, we have here, in this case, it is 2x plus 9. Okay, so we have to do nothing for this. So we write here 2x plus 9, and then du by dx means d by dx of u, and u we have is x squared plus 5, so it is x squared plus 5, and in between there is minus sign, so this is minus, put u again here, that we have to do nothing at this time for u, and then this is dv by dx, that means in place of v we have here under root of 2x plus 9, and whole thing is going to be divided by here according to the formula as v squared. So in place of v squared we have root 2x plus 9, so we put them a square, and now let's proceed further. So we have to do nothing for 2x plus 9 here according to the formula, but for x squared plus 5 we have to find the derivative of, so derivative of x squared is 2x, and for 5 that is constant is 0, then there is minus, we have to do nothing for x squared plus 5, and then inside here you can see that this is, it requires the chain rule, power rule, okay, or otherwise if you are fully, if you have fully command over all those sort of rule, you don't need to show the step, just you can write the direct sort of thing. So here you can see that in the first step you will have 1 by 2 because of the root, and then this is under the root 2x plus 9, and times it is, that after that in your power rule there will be derivative of 2x plus 9 only, so derivative of 2x plus 9 is 2, because the derivative of 9 will be 0, so it's going to be 2 over here only. So this is the derivative of the term under root 2x plus 9, okay, and whole thing is given as, here now it is a square of, this square root is, they'll cancel out root and square root and the square, so it is 2x plus 9 is remained here. And after that, what you can do, just solve it algebraically. So it's going to be 2x, and then times under the root, you have under the root 2x plus 9, and then minus, here we have to do a bit of the thing out here. So this is 2 and 2 cancel out, you can say here. So 2 and 2 cancel out, that means we have only 1 over there in the numerator. So this is 1 by under root of 2x plus 9, and the whole thing is going to be divided by here 2x plus 9. You can say this is the answer, but if you would like to go even further by solving it, so just what you will have then result like this is 2x plus 9 if you can handle algebra properly, So it is 2x plus 9 over here. So it is 2x plus 9, 2x plus 9. They got multiplied together. So it is 2x already here. Then a square and a square root will cancel out. So it's going to be 2x plus 9. And then it is only here minus 1. And now, if you like, you can break the bracket. So it is going to be 2x squared plus 2 times 9 is 18 and x and then minus 1. Okay, it's becoming in simplified form. All right, so we have multiplied this, and in the denominator we have 2x plus 9, and you can see here this is 2x plus 9 and this is under the root 2x plus 9. So one power will be added. So this is 1 by 2 and the other power is 1. So it's going to be 3 by 2. So you can write here this power is 3 by 2 and this is the answer. Right? And this is also possible that because the power is 3 by 2, so you could write this way also. This is 2x squared. No, it is 2 times 2 is 4. So there should be 4. Yes. So it's going to be 4x squared plus 18x minus 1 and divided by, also you can write here, this is the under root 2x plus 9 to the power 3 cube, and this could also be a kind of answer. So whenever you break the dy dx term and there is nothing asked in your question to show the result like this, okay, in that case you can decide yourself where you want to drop the answer. But good suggestion is that always try to express your answer in simplified form. So in this way we can prove both quotient rule as well as the product rule. And we also saw that how those sorts of formula or rules are applicable to the problem. I'm sure you are now able to understand how to prove product rule formula as well as the quotient rule formula. And also you have seen that in which situation those sorts of formula are applicable. If you have any question or any doubt, you can put your question in the comment box. I'll try my every best to get you back at my earliest. All right. So this is all for now, and thank you for watching.